This video is a quick introduction to a one-dimensional transient heat conduction simulator. You can find a link to this simulator in the description of the video if you want to try it out for yourself. So I'm just going to orient us first of all to the different parts of the simulator. So there are two panels. The left panel contains all of the settings that we can change to change the conditions being simulated, and the right panel is essentially a graphical output that shows the effects of those. So I'm going to go over different parts of the simulator and do a little test drive here to show you how it works. So in the settings side, it's broken up into three sections, and we'll discuss each of those sections. The first one controls the steady state transient nature of the solution to the equations. The second one controls the boundary conditions, and the third group down here controls the properties of the wall being simulated. So what we're doing here is simulating the transient, so time varying, heat conduction through a wall, or essentially through anything made up of layers of different materials. And I'll show you how to control what the layers are made of, how many layers there are, how thick they are, all sorts of things like that. Now on the right side, what it's going to tell us is the temperature profile through the wall. So what we're looking at first of all on the left side here is this is the outdoor temperature on our left and the indoor temperature on our right. And right now this particular wall is made up of two layers, and each of those layers is 20 millimeters thick. And this black line here is showing us the steady state temperature profile through that wall. Right now the indoor temperature is 20 degrees. We see that on this scale. The outdoor temperature is 0 degrees, and these two layers of material happen to have the same thermal conductivity, so the steady state solution is just a straight line temperature profile through both materials. Now other outputs that were given here, we're told what the heat flux through the wall is in watts per square meter. We're told what the R value of this wall is, both in English engineering units and also in SI units. Down at the bottom here, we're told what the interface temperatures for the steady state solution are. The locations referred to here are shown at the bottom of the wall here. So in this particular case, there's just three locations. The outdoor temperature, which is the 0 we talked about before. The indoor temperature, 20 degrees C, we talked about before. And because point 2 is exactly halfway between the indoor and outdoor locations, its temperature is just an average of those two, or 10 degrees. We're going to see this change as we change the inputs over here. So that's what we're looking at in the output section of the simulator on the right side here. Now we go over to the settings and see what we can change there. I'm going to actually do this from the bottom up. So the first thing we're going to look at is how to control the properties of this so-called wall. So the very first thing we see under wall properties here is just the number of layers that there are. And the default when you start up the app is 2 layers. So we have this light red layer here and this light orange layer here, both 20 millimeters thick. So we can change the number of layers by changing this input. Now for all of the inputs here, there are 2 ways to change these inputs. You can either grab and release the slider. I'm just going to put it back to 2 there, or you can type in a new number in the text box to the right. So either one of those will change the particular value of that input. So the number of layers here, I can just take this to 3 if I want, and now we have 3 layers, and all of the default properties and thicknesses just show up there. You can go all the way up to 4 layers if we want, or you can go down to 1 layer. So that just controls the number of layers. Now at any point, if we want to return back to just the default startup conditions, you can either reload the web page, which is easy enough to do, or you can hit this reset button down here in the bottom left corner, and it'll just get you back to these starting conditions. I'm going to do most of my other demonstrations here just with these 2 layers. There's no need to go to more layers to show how the simulator works. Now for each of these layers, there's a bunch of things that we can set. So you'll see a group of inputs here for each layer, and they're color coded. The first layer is this light red color, and the background of this layer 1 label here is the same color. So what can we control here? Well, we can control the thickness of that layer. So if I wanted to make that layer thicker, I can certainly make it thicker. So now it's 178 millimeters thick, and the other one is still just 20 millimeters thick. Notice the thickness of the walls is always scaled to give the same size of plot here. Just as this layer gets thicker, this one has to be shown thinner to fit it in the same scale. That's all. So I'm just going to reset back to original thickness. So the first thing we can change is the thickness. So that's the only physical dimension of the layer that you can change, because this is just one-dimensional heat transfer simulation. Now the other three controls here are properties of that layer. So there's the thermal conductivity, the specific heat, and the density. And these are all put in standard SI units for those three quantities. So we can change those any way we want, either with the sliders or by putting numbers in the text boxes. So by default, these just have generic properties in them. The other thing we can do is use this material drop-down box to pre-select those properties to a few common building materials. So softwood, fiberglass, styrofoam, and drywall are the only selections in there. So this is sort of set up to simulate the wall of a house or a building, but of course you can use it for any one-dimensional heat conduction situation with multiple layers. You just have to use the custom selection here to put in your own numbers. So notice when you choose one of these, so if I change this layer to softwood, then it changes to typical properties for softwood, and you can no longer change these. So the thermal conductivity, specific heat, and density are fixed at these generic softwood values. Now if you actually want to adjust these a little bit, these are close to what you want, but you'd like to have control over them, you can just go back to the custom and it reactivates these inputs, but leaves the same numbers as the previous setting, which was softwood. So you can now go in and change these a little bit if you have a slightly different type of softwood, for instance, than this generic values that are in there. So in that way you can make these layers whatever you want. So I could make this outdoor layer softwood, and maybe the indoor layer makes sense to make it drywall, I suppose. Makes sense to make it a little bit thinner. Maybe I'll make it 7 millimeters, and I'll maybe make this 100 millimeters, something like that. Okay, so this isn't really a real wall, but you sort of get the idea. Now that we have two materials in here with a different thermal conductivity, you can see the slope of this temperature profile is different in the two walls. So I've just hit reset here to get us back to our generic starting position. I don't want to change a whole bunch of things at the same time here. So all of these controls just determine the physical layout of this and what materials the layers are made of. Next thing we want to go to is the boundary conditions. And there are two different types of boundary conditions we can have here. Either wall temperature boundary conditions, which is the default that's selected right now, or air temperature boundary conditions. I'll discuss wall temperature boundary conditions first. Those are certainly the simplest. So there are two active inputs when we have wall temperature boundary conditions selected, the outdoor temperature and the indoor temperature. So you'll see right now the outdoor temperature is 0 and the indoor temperature is 20. But we can change this to whatever we want. If it gets colder, we go to -20 outside, and the temperature here changes to -20. So again, because we're just looking at a steady state solution right now, and we're looking at two layers that have the same thermal properties, then we just get a straight line temperature profile from -20 to +20 through the materials. Now the other type of boundary condition that we can put in here is air temperature boundary conditions. So now these two sliders sort of change their meaning. Now this is the outdoor air temperature, and this is the indoor air temperature. So rather than these being imposed as boundary conditions on the surface, on the outside surface and inside surface, these are now the temperatures of the surrounding air in the outdoors and in the indoors. So you'll notice now our outdoor air temperature is -20, and our indoor air temperature is +20. However, the wall temperatures, the outdoor wall temperature looks like it's about -10, and the indoor wall temperature looks like it's about 1 degree. So the meaning of these two controls has changed. So you'll notice now that we still have a linear temperature profile through the materials because they still have constant thermal conductivity, and in fact the thermal conductivity of the two layers is the same. But we now have a thermal boundary layer on the outside and on the inside wall. Please note that the shape of these thermal boundary layers, both on the outside and inside, is just a schematic diagram. It hasn't solved the equations of fluid mechanics or anything coupled with heat transfer to give an accurate temperature profile in that thermal boundary layer. It's solving for the temperature profile in the solid material accurately, but not the temperature profile in the thermal boundary layers on the outside and inside. So these are just little schematic diagrams representing the temperature profile. Now, if we go down here to our interface temperatures, remember that the outdoor temperature is minus 20, so the temperature of the outside surface, 0.1 here, is minus 10.8. So I had guessed at it as minus 10 before, but it's actually minus 10.8. Likewise, if you were to be inside of this room, put your hand on the wall, the temperature you would feel is 1.5 degrees, the indoor wall surface temperature. And again, the temperature in the middle is just going to be the average of those two, which apparently is minus 4.62. So that's the boundary conditions. So those are air temperature boundary conditions. Now the other thing to note here is once air temperature boundary conditions are selected, we have the ability to adjust the heat transfer coefficient on the outdoor surface and on the indoor surface. And again, when you first turn these on, just default generic values pop up here, but we can adjust these. So if the outdoor heat transfer coefficient, let's say that the wind started blowing outside quite strongly, well, that would increase the heat transfer coefficient on the outside. So I could take this heat transfer coefficient on the outside and increase it fairly dramatically from 20 up to 50. And we just noticed that the temperature difference between the actual air temperature and the outdoor surface temperature decreases because we've got a higher heat transfer coefficient, so we get a lower temperature change between the outdoor air temperature and the outdoor surface temperature. Notice that the heat flux also went up, so I'll go backwards here. So it's currently 214. If I were to go back to 20, then that heat flux would decrease down to 185 because the overall resistance through this wall is now changed. Now again, I'm just going to hit reset here just to get back to our generic conditions. So we're back to wall temperature boundary conditions, just going from 0 to 20 here. So the last section that we're going to talk about here is the transient and steady state controls. So everything we've done so far, steady state has been selected here, and all we're seeing over here is the steady state solution. So I'm going to go into transient mode now, and just do that by clicking this radio button, the transient radio button. Now you'll notice nothing happened here, and that's because it's not going to do a transient solution until we make a change in the boundary conditions. All right, so it's sitting here ready for us to make some change in the boundary conditions, and then it'll go ahead and do a transient solution from this current temperature profile to the new temperature profile that would eventually establish itself after a long time at the new boundary conditions. So what we'll do here is just change this to minus 20 degrees. Realize that this is just a step change. Okay? So we go minus 20 degrees, and as soon as I hit enter, it does the transient solution. So I want to orient you to what's going on over here. So this first profile, which is plotted in green, is our initial condition. And there's a little reminder down here, there's a key. So the green line is the initial temperature condition. So it's got actually a bunch of red lines plotted close to it, so it doesn't look very green except for this little part right here. But that initial temperature profile was our initial condition. The black line is still the steady state solution. So if we were to leave this wall at minus 20 on the outside and plus 20 on the inside for a long time, eventually the temperature profile in there would be that black line. So that's the initial condition and the final condition, or the steady state solution. Now what I want to talk about is the red lines that represent the transient, or the temperature profiles while this change is happening. So right now we have a bunch of red temperature profiles, and they're all crowded together down here. So I want to show you how to control that and make it so it's a little bit easier to see what's happening there. So all of that is controlled by these two inputs that have become active when we chose the transient solution. All right. So the two of those are the transient time step, which by default was 1 second. And so that essentially controls the space between these lines. So what this is doing is drawing a red line, which is a temperature profile, every second after that change in the outdoor temperature was made. So the very first line that we see here is the temperature profile after 1 second. And then the lines just progress after that. Now they're all smeared together here, you can't see them anyway. So there are 60 lines here, each 1 second apart. And the 60 comes from the second control. What is the total transient solution time? 60 seconds. So it just means that we need to make some adjustments to these two controls in order to be able to see a little bit more of what's happening between the start of this transient solution and the end of the transient solution. So I'm just going to make the time step bigger. I'm going to go to 5 seconds. And so we now have 5-second steps, but notice we're still only going to 60 seconds. So we clearly need to go a little bit longer in time. So I'm going to make this quite a bit bigger. Actually, I'm going to go up to 600. So we have 600 seconds that we're simulating, and we're going to show the contour intervals at 5-second intervals. So you'll notice that the last temperature profile plotted is now getting a lot closer to our final steady state solution. There's still a lot of lines there, so I'm going to actually increase this time step to 60 just so we can see the individual lines a little bit easier. So what we're seeing here is this first line is after 60 seconds, so after 1 minute, and then the very last line plotted here is after 600 seconds, or 10 minutes. So if the temperature outside were to suddenly drop from 0 to -20, then after 10 minutes, this would be the temperature profile in a 2-layer wall made up of these particular materials. And of course, you can do this solution for any number of materials with any properties that are within the capability of the simulator. Now, one thing I should point out is that the transient solution is just being done in response to changes in the boundary conditions. All right. So if I were to go down here and change, let's say, the number of layers, I'm going to change this to 3. So we'll see what happens. Well, it goes back to steady state solution. So it's not going to do a transient in response to a layer being added. It only does a transient solution in response to changes in the boundary conditions. So now that we have 3 layers, if we wanted to go back to a transient solution, we could. So let's say that it warms up outside again, back to 0 degrees, then that's what the temperature profiles would look like. If I wanted to change one of these materials, like if I go to the middle here and I say, well, I want to make this out of fiberglass insulation perhaps. So now notice what we have here. We have a layer of relatively high thermal conductivity on the outside and inside, and a layer of relatively low thermal conductivity in the middle. So you get a little more interesting temperature profile. So if I were to go back to the transient solution here and make another change, maybe back to -20, then we see the temperature profiles for the transient solution are being shown here. Now, I'm going to make this even a little more interesting. I want to go a little longer here, maybe 1200, and we can see inside of the materials, we get a fairly interesting temperature profile for the transient solution. So feel free to click on the link in the description here that'll take you to the simulator, and you can play around with it and get an appreciation for just how the temperature changes inside of a multi-layer wall like this in response to changes in boundary conditions and materials, if you wish. Well, I hope this is useful to you. Thank you very much for watching.